Hello and very welcome. This is the fourth lecture in our series of looking at application examples that Professor Nick Ravesh presented in his Planar Multibody Dynamics textbook, the second edition. And as you already know, he also coded these application examples in MATLAB as part of his dynamic analysis program, which he coded in MATLAB. So, today's lecture is also the 8th lecture in our postgraduate module Dynamics with the acronym msd780. And just to introduce myself, if you don't already know, my name is Dr. Lucas du Plessis, and I'm a senior lecturer in the Department of Mechanical and Aeronautical Engineering at the University of Pretoria. So, today we'll start with the application example named card_C. In the previous lecture, lecture 7, we looked at card_B, and in lecture 6, we looked at card_A. And you can see the schematic representations of the card in its assembled form here in figure 8.9a and in its exploded form in figure 8.9b. So card_C. This is a variation of the previous card models where an applied torque has replaced the driver constraint on the rear wheel. So for card A and card B, we had different driver constraints for this rear wheel being body number 2, and now we are replacing those driver constraints with an applied torque. So it is assumed that the torque is generated by an electric motor with a torque speed characteristic shown in figure 8.12, and we will also be looking at section 4.5.2. Okay, so this is the torque curve of the motor that will be driving the rear wheel. Okay, and we'll talk about the curve and the mathematical expression for the curve in a minute. Let's just look at this subsection 4.5.2 in Professor Nick Ravesh's textbook. The title of the subsection is Motor and Driver. So a rotary motor can be included in a multi-body model between two bodies about the axis of a pin joint. In most applications, one of the bodies is ground, as shown here in figure 4.18a. It's not always the case, and obviously for our card C, this is not the case. For our card C, the motor is connected between body 1, which is the main frame of the card, and body 2, which is the rear wheel of the card. But in many applications, one of the bodies is the ground, as shown here in figure 4.18a. A rotary motor applies a pair of torques on the two bodies that are equal in magnitude and opposite in direction. An idealistic representation of a motor with a known torque would be for the motor to generate a constant torque, or a torque being a function of time. For example, the torque may follow a non-linear function, which is given by this expression. Torque is a function of time. Now, in a more realistic representation of a motor, we should consider its torque speed characteristics. For example, figure 4.18b shows typical torque speed curves for two direct current motors. Okay, and this is the reference where Prof. Nick Ravesh got this information from. Design of Machinery, which is a publication by Norton. Okay, so we are looking at typical torque speed curves for two DC motors. This is figure 418b. The solid line, the linear solid line, represents a permanent magnet motor, and the non-linear curve, the dashed line, is for a compound wound motor. So either function shows that the torque varies with speed. As the speed increases, the torque drops, and vice versa. Okay, and this is clearly shown here in figure 418b, where the vertical axis is the percentage of the rated speed and the horizontal axis is the percentage of the rated torque. So, whether the torque is assumed to be constant or a function of time, or to follow a known torque speed characteristic, since the amount of torque can be determined at any given time and speed, we may consider such models in the category of applied force or torque. Okay, and we'll look at how this is implemented, how Prof. Nekravesh implemented this statement in the dynamic analysis program. Okay, so that was a quick overview of subsection 4.5.2, the motor portion of subsection 4.5.2. The driver portion of this subsection we've been discussing in previous lectures. So let's now focus further on the motor. The motor, represented by the torque speed curve shown in figure 8.12, can provide a maximum torque here on the horizontal axis of 20 Newton meter at zero angular velocity. In other words, where omega is zero. And this motor can reach a maximum angular velocity of omega max equals 4 pi radians per second at zero load. Okay, so in other words, where the torque is now zero. The motor can rotate at the maximum angular velocity of 4 pi radians per second without being able to deliver any torque. Alright, so now to find an expression for omega motor, let's consider the following. Okay, so we can say the angular velocity, omega motor, angular velocity of the motor, which is plotted or indicated on the vertical axis, equals the slope of this curve, which is the change in angular velocity. So it is 0 minus 4 pi or minus omega max. In other words, it will be minus omega max above the line, and below the line we've got 20 or T max minus 0. That's, in other words, T max. Okay, so this is the slope of this line multiplied by the torque of the motor, in other words, the value on the horizontal axis, the torque of the motor, and then plus the intersection with the vertical axis, which is 4 pi or omega max. That's just the equation for a straight line. It's simply the value on the vertical axis equals the slope multiplied by the value on the horizontal axis plus the intersection of the line with the vertical axis. Okay, so we can use this expression to find an expression for T motor. In other words, the torque that the motor can deliver. Okay, now in order to do that, we've multiplied all the terms with T max at the above the line and minus omega max below the line. Okay, so if we multiply this term with T max above the line minus omega max below the line, this falls away, this cancels out. Okay, plus the omega max multiplied by T max above the line minus omega max below the line equals, now on this side of the equation mark, we've got omega motor multiplied once again by T max above the line and minus omega max below the line. Now it follows then, so we've got T motor equals T max. Remember this, we cancel out the omega max, but the minus will remain here. So if we take that minus T max to the other side of the equation mark, it becomes positive. So T motor equals T max, and then just rearranging the terms in this term over here, we've got minus T max omega motor divided by omega max. And of course we can simplify this to what you see on the screen at the moment. T motor equals T max multiplied by, in brackets, 1 minus omega motor divided by omega max. Okay, and this is the expression that Prof. Nikravesh uses in defining the torque that is applied on the rear wheel, which is body 2. Okay, but we'll look at that in a minute. Okay, so let's look now at exercise 8.9. There are 3 tasks for us to complete. The first is simulate the dynamic response of this model for 6 seconds. Now before I do that, we are also going to review the input M files for this model. Okay, so what you see on the left of the screen is the first input file in Animate. These points anim is exactly the same as for card underscore A, which we discussed in lecture 6, and card underscore B, which we discussed in lecture 7. The same is true for bodies 1, shape, width, height, and color. The detailed explanation is given in lecture 6, where we spoke about card A, and the same goes for bodies 2 and 3, where we mentioned in both lecture 6 and 7 that for the radius we need to specify the value for the radius as a 2-element row vector. Okay, otherwise we get an error message. Okay, so nothing strange there. What I did do is I changed the value for X max for the defining the 3D animation axis. I changed that to 8. So the value that Prof. Nikravesh used originally, I think, was 3.5, and that's too small for the animation. So all I did was I changed it to 8. Okay, and one could, for that matter, also put in 8.0. Okay, nothing wrong with that. Okay, so in bodies, this is also exactly the same as for card underscore A, discussed in lecture 6, and card underscore B, discussed in lecture 7. In forces is different. Okay, now we've got not only weight acting on the system or mechanical system or card, we also have this user type force that we define here. Okay, and as you can see here at the bottom, so forces now has 2 entries, F1 and F2. Alright, so while we're there, let us look now at this user force and how Prof. Nikravesh implemented it and coded it. So there's an additional M file which is titled user force. Okay, and this is now our motor. So if I can go back to this quickly. Okay, he defines omega max as 4 pi. Okay, he defines T max as 20. Then he says omega, so in other words, the angular velocity of the motor is the absolute value of the second body, angular velocity P underscore D is the angular velocity element of bodies 2. Okay, so to understand this bodies 2, why is it bodies 2 dot PD? Let's look at Appendix B, the user manual for the dynamic analysis program that Prof. Nikrewesh wrote. Appendix B. So if you look at the structure body, you can clearly see here in table B.1 that bodies or dot PD is the time derivative of phi of that body, where phi is the orientation angle. So that clarifies this portion of Prof. Nikrewesh's user force function. Then the next statement says the torque of the motor equals T max multiplied by, in brackets, 1 minus omega divided by omega max. And this is now exactly this formula that we spoke about a moment ago. T motor equals T max multiplied by, in brackets, 1 minus omega motor divided by omega max. Okay. So then Prof. Nikrewesh has an if statement. If the torque of the motor is greater than T max, okay, then the torque of the motor must be equal to T max. Okay. And then these two statements are also very important. Bodies 2 dot N, okay, that's the external torque that is applied on the body number 2. Okay, so it is whatever the external torque is minus the torque of the motor. So why is it minus? It's because this torque is applied in a clockwise direction. And if you remember our sign convention, clockwise rotations are considered to be negative, and that's why it's minus that torque. Okay, and we have to also define the reaction torque on body 1, okay, which is then bodies 1 dot N plus the torque of the motor. It's the opposite direction of the torque that is applied on the wheel. Okay, so that was the input file user force. We looked at forces. In funcs is supposed to be an empty M file, so I just made a correction. The example that I had on my version of Prof. Nikrewesh's code listed F1 as an A-type function, which is not correct. Okay, so it's supposed to be empty. This the program still runs perfectly even though F1 is defined, and the reason for that is because this function F1 is not referenced anywhere else in the input files. So, but anyway, technically speaking, this is what the input file in funcs should look like. In joints, this is now slightly different from cart underscore A and cart underscore B. And the difference is we now only have 4 joints. So we've got the 2 revolute joints, exactly as for cart underscore A and cart underscore B. And we've got these 2 circular disc joints, also exactly as for cart underscore A and cart underscore B. But if you remember, then for cart underscore A and card underscore B, we had a relative rotation joint, because that's how we defined the driver function on the rear wheel. Okay, and now since we've specified a torque that is applied on the rear wheel, we no longer need the relative rotation joint in the input file in joints. In points is exactly as card underscore A and card underscore B, and in U vectors is also exactly the same. There are not any U vectors that need to be specified. So we're now ready to run the simulation. In order to do that, we enter the acronym DAP. The folder is card underscore C. Do you want to correct the initial conditions? Yes, we do. Just to pause there, you will note that the corrected velocities are 0 as expected. The car starts from rest and the torque is then applied and the car then starts moving. So this makes sense. Our final time is 6 seconds and I'm using 0,1 as a reporting time step. Okay, so once it's finished the simulation run, you type in the abbreviation anim for animation. Okay, we can maximize it. Press any key to continue. Really only a sanity check to see that the mechanism behaves as we've expected. And you could clearly see from this animation, the initial part of the animation was not shown, but the card started from rest and then it ran in a straight line in the x direction with the y value being 0. So it runs along the x-axis, global x-axis, all the way to almost 8 meters. Okay, this is x, this is the x value, and that's the y value. Alright, so that gives us confidence that our simulation was correct, because the animation of the simulated results behaves as we expect. Okay, so now let's look at the angular velocity of the rear wheel versus time. Now the command that I'm proposing to do that is plot, open the bracket, T for all the reporting time instance, comma, PD, open the brackets, colon, comma 2. So to explain where this PD comes from, once again looking at Appendix B, the user manual of the dynamic analysis program that Prof. Nikrovich wrote. It's Appendix B to the textbook he published. If you look at table B.10, there is PD, this is the rotational velocities. So the NT is the number of time instants, and that's why in our case we will use colon, because we want all of the time instants or values at each time instant. And we're looking at body number 2, NB being the number of bodies. Alright, so that makes sense. In order to run that, we first need to enter the abbreviation POST for post processing. Okay, and then we can copy this command. Okay, so you can see clearly this is now the angular velocity of the rear wheel. So it starts at rest, it starts at 0, it then rotates clockwise, and it has a clockwise acceleration till it reaches the maximum angular velocity of the motor, which is connected to the rear wheel, and that is 4 pi radians per second. And here you can clearly see 4 pi if you do the calculation, and I'll show that. I've copied this figure 1 that I've just generated into my mind map, and I did that to compare it with the solution that Prof. Nikravesh published in his textbook. This is now the solid line in figure 8.13a. We'll speak about the dashed line in a little bit. So the solid line, you can, well, more or less see that it corresponds to what we have here. The scales are not exactly the same, but the comment clarifies the behavior. The rear wheel, which is body 2, as we already know, starts at rest and reaches a maximum angular velocity of the motor, which is minus 4 pi, and that's approximately minus 12.57 radians per second. So let's now look at the last task of exercise 8.9. We want to plot the velocity of the main body in the x direction versus time. This main body of the cart. In other words, that will be body number 1. Okay, so the command for that is plot, open the bracket, t, all the reporting time instants, comma rd, open the bracket, colon, comma 1, comma 1. So to explain this rd, where that comes from, once again referring to Appendix B of Prof. Nikravesh's textbook, the user manual for DAP. If you look at table B.10, then the translational velocities are listed as array RD. Okay, and that array has a value at each reporting time instant. That's where the colon comes from in our command. The number of bodies, so we are looking at body number 1, that's why the 1 comes from, and we're looking for the velocity in the x direction, and the x component is component number 1. That's where the last 1 comes from. Okay, so if we copy this command into Octave, right, so looking at this graph, the cart in the x direction also starts at rest, it starts at 0, and then the x velocity increases, it is positive towards the right, and that's where that's the direction that the cart is moving in. So that's why we've got a positive velocity or x velocity, and it reaches a maximum at approximately 3 seconds. Okay, which if we look at the this behavior of the x velocity of the cart corresponds to the angular velocity behavior of the rear wheel. At around 3 seconds, there is a convergence, if you like, of the angular velocity as well as the x velocity. Okay, so once again I've copied the figure 1 into the mind map so that we can compare it with the solution in the textbook. And this is now the solid line in figure 8.13b, and the same problem as before. We don't have the similar scaling, but it is, one can see if you eyeball or approximate the results, you can see that the behavior is the same. Okay, so the card is initially at rest, but after approximately 3 seconds, it reaches a constant speed. Okay, so let's now look at card D, the simulation variant of the card model that we've been discussing in the last few lectures. So in this model, we add a resistive force to the model of card_C. Assume that the forward motion of this vehicle is opposed by aerodynamic forces that act on body 1. If you remember, body 1 being the main frame or the body of the cart. Okay, so now to explain that further, the aerodynamic force can be represented by a simple model as superscript aero F, in other words, the aerodynamic force, equal to CV squared, where C is a damping coefficient as a function of drag and surface area, and V is the speed of the vehicle. Right, so that's how we're going to implement it. Let's have a look at exercise 8.10. So 3 tasks that we are supposed to do. The first is to simulate the response of the model with the resistive force for 6 seconds. So before we run the simulation, let's quickly run through the input M files. I've opened them here on the left hand side of the screen. All of the files except for one file will change. Okay, so in animate is exactly as I've discussed for card_C, same for in bodies, same for in forces, in funcs, in joints, in points, in U vectors. The only difference is this function user_force. So now we have the motor as we had for card_C, and we have an aerodynamic resistive force. Okay, so looking at the equation that Prof. Nikravesh provided in his textbook, the aerodynamic force equals CV squared. He defines in the MATLAB input file user force the damp aero coefficient as 10, and then he defines or isolates x_d as bodies 1.rd, 1. Okay, and that is obviously the velocity of body 1 in the x direction. Just to confirm that this is indeed the case, let's have a look again at Appendix B, Prof. Nikravesh's user manual for his dynamic analysis program. It's Appendix B to the textbook that he wrote, and we are looking at table B.1, the structure called body. And here you can see that R_d represent the time derivative of x and y. So we are interested in the x component, and that's why we have this index here as number 1. So it's RD, the first component, which is the x component, and this is obviously of bodies 1, which is the main frame of the cart. The next line of code is simply duplication of the formula that's given here in the textbook, F arrow is the damping arrow coefficient multiplied by the x velocity squared. Alright, and then as with similar to what we've done for the motor torque acting on body 2, we now have a resistive force acting on body 1, and that is now this F arrow, which we subtract to the already existing external forces acting on body 1 in the x direction. Okay, so with that said, we're ready to run the simulation. So let's do that quickly. We can enter DAP. It is card_D. Do you want to correct the initial conditions? Yes, as before and as we expect, the corrected velocities are all 0. This is exactly what we expect will happen. We will run the simulation for 6 seconds, and let's use a reporting time step of 0,1. Okay, now once again as a sanity check, let's do the animation. So we type in the abbreviation anim for animation. Okay, there's the error. This is maybe this is good, it happens. This is the error that you get when R in the input file in animate is not specified as 2 values. Okay, so I'll quickly correct that. Yeah, so this needs to be 0.1. And this needs to be 0.1. So I'll save that input file, go back to the command window, clear the workspace, clear the command window, and just enter all the commands again. Yes, we do want to correct it. 6 seconds, 0,1. Okay, and now we say anim, and there you go. We know sanity check wise everything looks fine. Now we want to plot the results. Okay, so I'm going to close this window. Now it asks us to plot the angular velocity of the rear wheel versus time and compare the results against those obtained without resistive force. Okay, so in order to do that, I will clear the workspace, clear the command window, run DAP, and run card_C. I will correct the initial conditions. Final time will be 6, the reporting time step 0,1. Now I'm not going to run the animation because we already know that card_C, there's nothing wrong with it, everything looked correct, and everything, we have confidence that our results are correct. Okay, but what we are going to do is we're going to run the post processor, and then we want to run this command over here. same as for cart underscore C. For the angular velocity, we plot time, the reporting time instance versus the angular velocity of body 2. Okay, so if we enter that, that's what we got for cart underscore C. Now we say hold all. So we want to freeze that plot of the angular velocity of body 2. We then enter, we clear our workspace again, we run DAP. Now we say cart underscore D is the folder which contains the model. Yes, we also want to correct the initial conditions. The final time will be 6. Reporting time step 0,1. We run post and we will run this command, but we will add the fact that we want it in dashed lines. Okay, so this part is added now. Okay, so let's enter that and then we can look at the results. Okay, so this is what I've copied and pasted in the mind map, and this compares perfectly with the solution that Prof. Nikravesh presents in planar multibody dynamics figure 8.13a. This is now the dashed line, the results superimposed on the results with no resistive force, and we observe a reduction in the final speed of the cart. Okay, so the angular velocity of the rear wheel is now less or is smaller than the angular velocity without any aerodynamic force. Okay. Following the same recipe for the velocity of the main body in the x direction versus time, the same recipe as I've just added, the command is just different. Okay, and the results once again compare perfectly with what Prof. Nikravesh is presenting in planar multibody dynamics. We can see a reduction in the final speed of the cart. So with that said, it's been quite an extensive investigation of this cart example. We looked at 4 variants of the cart, and it is to demonstrate the capabilities of the dynamic analysis program, as you already know. And I don't know about you, but I am certainly very impressed with what Prof. Nikravesh has achieved, and excited to use this tool and to expand on it further. So I hope you share my excitement, and with that said, thank you very much for watching.